it is to define the long-term stability, for example, slope. So the slope will fail in after years has been constructed. So meaning that after long period of time, and the stability of the soil on part of the sharing is become decreased. But in contrast to the deep excavations, for example, the critical point during the constructions, it means that the short-term stability. So because it increased the effective stress. So you have to choose correct constitutive soil model that can be explained or describe and predict the behavior of the soil subjected to the loads. So this coming to the stress strain, deformation, and etc. So the modified Kempley model is an incremental hardening softening elastoplastic model. So its features include particular form of nonlinear elasticity and hardening softening behavior governed by volumetric plastic strain. And the basic modified Kempley model includes parameters such as the initial void ratio, compression index, and swelling index. So I hope that you are very familiar what is the initial void ratio, compression index, and swelling index. So these are two parameters, compression index and swelling index. If you having some sort of the 1D consolidation parameter and you want to analyze part of the behavior of the soil subjected to the loads applied, they resulted to the consolidation stages, so you can have the compression index as well as the swelling index. And the deformations coming to you, the change of the volumetrics. So the originals or the size of the sample of the soil has been changed, and also the volume change. And the volume change can be captured through the relationship between volume versus strength. So the model here for modified chemically is consider the effect of primary and secondary consolidations, yielding and critical state behavior. It is often used to predict soil settlement and strength characteristics. So this is why mostly when we have a clay soil, so we want to estimate how long or how does it can go to settle, and how long the consolidations will totally completed. For example, on part of the consolidations, there are few types. For example, we have the immediate consolidations or immediate settlement. We also have the primary settlement, and finally we also have the consolidations or secondary settlements. So every type of the settlement we explain differently according to the soil strength and also the soil stiffness or elastic of the soil parameters. On the left figure here explains to you the difference of the yield criterion from original Chemclay and also to the modified Chemclay curve. So if you look at to the red color curve here, that's represent to the original Chemclay, which is in shape of elliptical. However, the modified Chemclay shows you the yield curve in the semispiral or semicircles of the yield surface. And how do we get the failure of the line or failure of the soil? When you have a maximum shear stress or maximum diabatic stress of the samples, and then tangent to the maximum diabatic stress, that is the line or critical state line. So the M is a tangent of the critical state line. So again, I explained earlier. So the modified chemically model, it is derived from the critical state theory. So the critical state theory here, if you can go on the right figure or here, you can see how it is explained the changes in the volumetric strain and also the changes in the initial stress applied to the final initial to the final stress applied to the soil until it failed. Here you can see the critical stress path from beginning of the stress applied, initial stress at point O, and then increase to the point D and up increase to the point E. You can see as well the changes in the volumetric strain at the low figure graph here. From the point of figure A, B, and finally is produced to you one another graph that we have E versus lone stress. So this actually can be obtained as well from one-dimensional consolidation test. So one-dimensional consolidation test will explain to you this relationship between void ratio and also the lone stress. And what we are looking here, there are some parameters involved in the critical state line in order to explain the hardening, plastic hardening point, as well as the yield criterion point. In totally explain to you the behavior of the clay according to the modified template as well as the template model. If you look at to the notes given here, there's some deriving formula to explain about the modified template, which proposed or which introduced by Berlin Roscoe in 1988, in 1968. So it assumed that the plastic behavior is a pre-failure deformation using an elliptical yield surface. You can see in the figure 6.12 here. And then it is also derived to the equations as seen in the 6.13, where the equation is a q square over m square p effective square plus 1 is equal to p effective c over p effective. P effective is a mean stress, and then P effective C is a pre-consolidation stress, and Q square or Q is a deviatory stress. So you can see here. So the serving as a hardening parameter is called here as a pre-consolidation pressure. And the volume from the equations of the virgin compression line can be obtained as a volume C is equal to N minus lambda ln PC. So these are equations that we're going to have from the critical states line in order to explain the clay behavior under modified template model. So the failure takes place when the stress rate PF QF reaches the critical state line CSL, which in the triaxial stress space is identical to the Moore column failure envelopes. So it states that finally, whatever you have from the complex triaxial plotting on part of the soil behavior when subjected to loads, it also can produce to you a similar or what we call it as a linear equation that also can be found from the Moore column model. But this is a very good model compared to the Moore column because it includes the plastic behavior, or what here we call it as a hardening parameter. And it also get involved to the critical states line because in the Moore column model, it is cannot explain to you where is the critical point of the soil condition when subjected to loads. And here, when you have the modified Chemclay, or you have the Chemclay model, it can give you ideally what's exactly happening on soil during the shading or during the applied loads. So this is true when we look at to the soil behavior. Uh, Initially, we have the stress point here, and then we have the initial deviated stress. At one time, when we increase the stress or increase the loads until it meets to the final lines or until it meets to the maximum point lines. So that is the critical stress, or we can have that's meaning to the critical states line. So the critical states line here can be given to you one equations where the QF at final is equal to MP effective F. So this is a like of linear equations, a simple linear equation, but includes all the importance parameter of the clay behavior. So since this is not enough, if you only display for QP stress bars, you need to also include the effect of the volumetric strains. So the volumetric strain or stress deformation space can be explained through the equations 6.16, where the volume is equal to the kappa minus lambda ln effective P at final, where the kappa is equal to N minus lambda minus. In this case, a kappa, and here is another parameter's names, ln2. So these are similar things that we can have from the figure 612b. So actually, the equation 6.16, 6.17, and also 618 are deriving from the figure 6.12b. So if you look at this figure, actually we only have firstly at the virgin consolidations line. So the virgin consolidation line explains to you the stress behavior in the normal consolidated clay. But then when the soil decreases in strength and meet to the critical line, this is the conditions where we have the reloading or we have some sort of the swelling conditions or swelling behavior, then we can get the critical state line. And also these two lines, VCL or CSL, can be given to you these two equations and also the parameters. So the initial stress state of the one-dimensional considerations as given here, the P effective node and then the Q node. So the corresponding initial volume can be found from these equations. And then when we rearrange these equations, finally we can have another equations which in 6.21. And also during the unloading to failure, during the undrain loading to failure, the initial volume V naught does not change. So this is the assumptions, and we can have the final mean stress as given in the equations 6.22. And what we want to see is actually is the final derivatives mean stress, and also what we want to find at the final is the mean stress and also the derivative stress as given from equation 6.23 and also 6.24. And when you combine all these equations using 6.7, 6.9, and 10 to the 619, we can transform the equations for undrained cohesion is equal to K times effective V naught. Effective V naught is the effective overburden pressure. Remember last class I told you if you have some sort of the unique weight of the soil and then you know the depth of the soil layer, you want to estimate the effective overburden pressure. And if you have the effect of pore water pressure, you need to minus the total stress minus with the unit weight of the soil, unit weight of the water, so you can have the effective overburden pressure. So the CU can be used to replace or to use this kind of the empirical equation to find the undrained cohesion if you do not have any other kinds of the site data. Okay, the K, what is the K? K can be found from here, where the KMC is calculated from equation 6.12, and the typical range value according to the effective phi, and also this ratio between kappa and lambda. So we can have the K is equal 0.215 to 0.251. And finally, if you include the effective adherency response curve to the left equations, which means that you want to see the behavior of the soil at the left side or at the right side, wet side or dry side, we can use this kind of equations. So here we can see the effect of the derivative stress, mean stress, and then the void ratio. The original Camplay model, you can see from here, is very simple, straightforward, not so complicated compared to modified Camplay. However, some limitations not include to the effect of the plastic strain or other kinds of the hardening parameters. So in the summary, it is necessary to determine earth pressure under undrained loading conditions because this is a very critical stability of the soil during the time of the constructions. So the total stress analysis is probably the easier way to calculate this pressure. The effective stress analysis in principle produce the same result, provided the chosen soil method is capable of accurate predictions of the undrained shear strength. It is shown that more column model overpredicts the undrained shear strength by as much as 50%. In contrast, both the original and modified Camplay model produce very close predictions, both within 1% of the experimental data, in spite of the fact that their analytical expression look very different. Yes, it is true because some geotechnical engineer or any practitioners engineer, they're afraid to use advanced consistency models such as original Camplay or any kind of the model because it's difficult to find the correct value of these kind of parameters. For example, you want to get what is the parameter of a lambda, what is the parameter of the kappa, and then you want to find exactly the calculations to estimate void ratio at final, initial, or void ratio every stage of the pressure applied. So as part of the mathematical itself, part of the analytical equations is difficult, but to ensure the stability of the structure or whatever it is very good to use the advanced consistency model, and the experimental data can provide you this kind of data parameter model, but need to do some verifications and validation before use in the design stage. Okay, this is again why we just explain the things about molecular model and also the modified chemically and also original chemically is that the modified chemically showing to you that the critical or the critical part of the soil is actually reached to the critical state line in the curve shape. However, for molecular model, it's assumed that the maximum or the failure point meet to the critical line vertically, which over predicted this the undrained strength of the soil. So when we have this kind of high value of undrained cohesions, it says that the structure is safe. However, in the real conditions of soil at the site, it is not truly present what we have designed. So when you have these kinds of problems, so it's better to recheck, redo, redesign based on the current or based on the real-time data, so that we can have some sort of early warning sign or early mitigations to ensure our structure will be safe during the construction time or after few years construction time. So the drain case for pure shear would not cause any volumetric strain. This is true. However, in undrained shear loading, when no volume change is allowed, this result is no pore water pressure being generated. The mean effective stress P prime stays constant, and the corresponding effective stress path to failure in P effective Q triaxial stress space is vertical, as given here. For normal to slightly overconsolidated clay have a tendency to contract during drain loading since the water is incompressible in undrained shearing. So the result in positive excess pore water pressure. So the corresponding effective stress path to failure in effective P to Q triaxial stress space curve to the left from vertical. This is what exactly occur or when you have from the modified template or original template. Okay, how about the analysis? If you use the simple analysis or simplified model, this is what we're going to have, where we assume that from 1 to 6 strut in 19.2 meter depth, that is the upper marine clay as given the soil parameters such as 16 kilonewton per cubic meter, and then effective phi is a 22 degree, undrained coefficient is 20 kPa. So effective phi is internal frictions angle between particles, and this is the undrained coefficient of the clay, and this is under the effect of the water table. And these are the parameters for lower marine clay, and the total depth is around 12.8 meter. Before we can do the analysis, what we need to find is the parameters of the soil from elastic parameter as well as from the shear strength parameters. So the value of the strength soil can be obtained from the SPTN. SPTN is some sort of the soil investigation testing, or what we call it is the standard penetration test testing that can give you the soil profile as well as the soil depth. So the depth of the soil or the soil profile can be determined from the SPTN number and also the bearing capacity of the soil at particular depth. So here, since this is the short-term stability, the short-term stability is actually can be applied to effective stress, or it also can be applied for total stress. So this here, you can see that the data for coefficients is using by undrained coefficients. So the coefficients here is 0 from the top until to the few bottoms below the ground surface. Then they can found 5 kilonewton per square meter and 5 kPa, and finally 10 kPa. So it is the value here indicates the soil is very soft soil because the strength only can be captured at the few meter below the ground surface, and it is rely on the internal frictions angle. The elastic modulus can be seen from here, and the permeability of the soil. So you can see that the permeability of the soil from the top, since this is clay, so you can see that the power is quite low at the beginning and then increase to 10. So mostly in the clay, the permeability of the clay is very low. So the groundwater level here is considered to be at the soil surface. As you can see here, this is the groundwater table effect at the ground surface. And the parameter simplifications as shown here, the shear strength undrained is 20 kPa for the upper marine clay, and then 38 kPa for the lower marine clay. And from the table as well, it is estimate from the field test and the original design estimate that the undrained coefficient is equal to 0.21 effective V naught. So this is what the estimate at the early design for normal consolidated clay soft marine, which was based on the assumptions of the hydrostatic pore water pressure. This is because the lower marine clay is still undergoing consolidation from the land reclamation of 1970s, and it is under consolidated. So consolidations is actually can be occurred for a few times years ahead. So we could not say that consolidation finished at one particular time. Sometimes it's already occurred, but since there is some stress removal, and then there's some sort changing in stress history, stress conditions, so the consolidation still takes place. So that's why when you have some sort of constructions near to the soft clay or near to the soil, so please make sure do the soil treatment or soil stabilization first before you do the constructions. So the excavation is assumed to be supported by 10 strut levels spaced vertically at equal intervals of 3.2 meter. So the first strut level was located 1.6 below the surface, and the surface surcharge is assumed to be equal to 0. So indeed, in this case study, it assumed that the surcharge has no effect. Basically, surcharge can be included in the analysis to counter the additional stress to the soil. So the last 10 strut level was built after the temporary JGP slab at the same level was removed. So if you can have some idea the construction stages of the material, you can see at how it was started. So it start by excavate and then apply struts, and then they also place the JGP, and they supposedly remove once it's reached to the final strut number, which is 10. Okay, this is also a table of long-term stability strut loads with the factor of safety 1.0. And then EAU is the lateral pressure for this problem. So you can see that for these kinds of the deep excavations, the pressure of the soil is not likely as a triangle shape. So it will be differ according to this soil pressure, and then the strut force acting to the soil wall, and then the calculations of the lateral pressure can be found or can be calculated from these equations. So you can see that on part of these equations, the difference of the coefficients of the active earth pressure Ka1 is used at the ground surface or at the upper marine clay, and then Ka2 will be using for the lower marine clay, because the properties of the cell are different even though it is also same in the clay group. Wait a second. Okay, when we look at here, the total design for strut loads around 14,752. So this is the design value for long-term stability analysis for strut loads. If you can compare for the next short-term stability, you will see the difference of the strut load applied. So in here, the total safety factor is around 2.14, which is a ratio between the total load strut 14,752 over with the EA. So you can see as well, the design estimated the value of the strut force higher compared to the estimated or the calculation one, which is quite low. The strut force is quite low, meaning that it cannot support the loads applied to the soil actually. But the design say the strut force is capable to support the loads, or the strut force is higher. For short-term stability, you can also see the lateral pressure in totally different shape. Now it's not a straight rectangular from the top to bottoms. So you can see half portions of the trapezoidal in upper clay and the rectangular shape at the lower marine clay. So there's some sort of theoretical background how it can be derived in this pressure diagram shape for upper layer and to the lower layer of the marine clay, because just now we have seen for long-term stability, and right now it's a short-term stability. So looking here, the factor of safety for short-term stability is very low compared to what we have for long-term stability is at 2.14, meaning that the deep excavation is not critical for long-term stability, but it is critical in the short-term stability. And you also can see that the total active load bearing is around 11,717 kilonewton per meter, which a bit higher, even though it is a bit higher, but the factor of safety shown differently. And this also showing to you a table of the strut load for short-term stability, which the strut load's total load is 11,717. And if you look at to the right side of the figure, this is a comparisons between the designs graph and also short-term and long-term stability. So the short-term stability showing that the strut loads has high forces compared to the long-term, and but still it is quite lower from the design's estimations. So again, since here after failure occurred, then do the forensic investigation or back analysis, they found that there's some misdesign of error found from here. The other just now is part of the stability analysis. Now you look at to the excavation progress and collapse, because we want to understand how it was occurred. Is it the failure occurred in stages, or the failure occurred in one time occurred, or in one time effect? So from here, you can see that the evaluations of the total pressure with the progress excavations as shown in the figure 6.18. So which apply the diagram from figure 6.16. Stepwise increase in depth. So the corresponding strut loads at various stages of excavations are shown here. So meaning that the strut loads apply, and then the depth increase, which give you a difference of the forces or different stresses occurred behind the excavations. So this is also similarly can be explained or can be seen from the graph plot here. How does the strut loads forces change according to the depth? So you can see that when the depth increase, the strut loads theoretically also increase, but it also increased by the stage of the construction. From the first stage of construction, stage 1, stage 2, 3, 4, 6, and then the depth of the strut load from the ground surface to the final strut load are totally different, because you can see that the increment of the depth, even the Z is equal from the strut loop strut 1, strut loop 2, the Z is equal, but the depth applied here change differently, but since can be given as a linearly. When you increase the depth of the penetrations or the excavation depth at the different stages, so it also increased the strut loads. So the analysis from the excavation progress and collapse, you can see here at the strut load number 6 is actually showing to us the critical point that actually started to collapse. So this is what they found from the original or from the design itself. And again, if you compare to the short-term stability and long-term stability, it doesn't shown as from the design curve line. The excavation progress, the load in the 6 struts level approached the design load, and this was exactly the location where the structural buckling problems had been encountered in February 2004, 2 months before the collapse. And the critical stage of excavations, removal of the temporary JGP slab before the installations of the 10 struts level is shown in the figure 620A. And the strut slopes before and after the removal of the temporary JGP slab are compared to the design strut slopes. So it can be seen as the slab was removed, and if it is full load were transferred to the 9 struts level, the design load in the 9th level would be exceeded by 15%. Together with the structural error in the wall beam design, this would lead to the 9th level failure, and the load then would be redistributed to the 8th level strut as was indeed measured, which would also fail and causing a progressive collapse of the entire strut system. So it says that the failure is not occur at one time. So it occurred progressively, but no one noticed the changes, or no one noticed from the monitoring data is actually the early signs the failure started to occur. And this is also explained when we remove the JGP slab and what exactly happened in the stage 10. So you can see that there's nothing much change at the strut slopes. So it's true the failure is not occur at the stage 6. Sorry, the failure started to occur at stage 6 or at the strut 6, not in the stage 10 or at the strut number 10. So from the analysis, we want to see on part of the design error factor. Firstly, it is say that it is claimed the wrong choices of constitutive soil model. Why is this that? Because using the more column, it overestimated the undrained strength of the clay. So the designer used the undrained coefficient for upper layer is a 30 kPa, meanwhile for lower layer is a 66 kPa. What exactly from the SI reports, the original data for upper clay undrained coefficient is at 20 kPa and the lower clay is at 38 kPa. So this is quite double estimations from the real one. So that's why the more column, considering as well the assumptions in the model itself and where it assume the critical line and the path of the critical line vertically, which shown incorrectly to the real soil behavior in plus with the overestimations of the undrained coefficient. That's why the previous designer said the design was correct. However, after failure occurred and they did on the investigation, they found that, or they did on back analysis, they found that actually the data parameter used for the design was overestimated. And the other thing is that due to the incorrectly calculated total active load being given here as a 10,090 kilonewton per meter, and the total active load is 11,717. So let's say this assume that the value is 10,000, and it is also underestimated about 17% and the load in the critical lower part of the excavation by almost 30%. So parameter they estimate over, but the actual strut load they underestimate. So when these two combine together, they resulted to the collapse failure. And not to forget here, if you look at to the effect of the JGP, when the loads are underestimated, as seen from the case more column, the removal of the JGP slab does not cause the failure of the ninth level strut. So indeed, even if the full load of the JCP slab is transferred to the ninth strut, it loads to the strut load, which is 13% smaller than the design 13% smaller than design loads. So this is hardly surprising because the design was based exactly on this underestimated strut loads and their redistribution during the removal of the JGP slab. And it is true from the back analysis shown that the JGP does not give any effect to the failure. And this is how it says that on the average coefficients for upper and lower clay layer. What can we conclude from here is that overestimations of undensure strength resulting in the underestimations of the active earth pressure was one of the major reasons for the nickel highway excavations collapse. So the buckling of the walls in the 6 strut levels and the critical effective of the removal of the JGP slab can be other factors considered to the failure. It was inappropriate use of the more column model in the finite element analysis that brought this tragedy. If the design was based or at least compared to the above simplified analysis, it could urge the designer to review the FE calculations. So it says that you want to use the numerical simulation, it is welcome, but you need to verify the output or the results from the numerical simulation using the simplified method or using any other analytical equations or mathematical equations. So when you have the verifications data, you can confirm your design is right. But if you are not doing the verifications or validation data, so we can't ensure that our structure is safe. So what are the mitigation measures? So these are some mitigation were taken during the time. For example, the damaged canal in the collapse area was blocked up to the prevent tidal, and then they covered the slope using the canvas sheet. And what other things? The crack in the ground around the site were filled with the grout to prevent water seepage. So these are the activities were carried out during the time, and surrounding buildings were inspected to ensure they are safe to use, and the buildings continually monitored and checked around the clock, so that the thing needs to be done. And additional settlement marker were installed near the building, and additional inclinometers were installed to monitor the lateral deflection in the soil. And also they need to capture the other factors such as water pressure and any related to the mitigation work to prevent future failure. So if you look at to the construction stages, but here we're talking about the recovery stages. So for the recovery stages, there were 9 stages involved. Firstly, you can see that they perform foam concrete at the lower strength and low viscosity concrete to filling the immediate collapse. And then they stabilize the void and prevent further soil movement and subsidence of the surrounding ground. And the low strength of the concrete mix allowed to be removed later when excavation recommenced following the recovery process. And the next one is that they carry out localized filling of mass concrete, backfilling of soil to stabilize the outer areas of the collapse slope. In the 4th stage, to remove whatever debris still be that could be from the top. And then in the 5th and 6th stages, were to backfill with the soil below the nickel highway and above the incident site of the original ground level. And in the 7th stage, reinstate the nickel highway. And finally, in the 8th and final stage number 9, the instructions was to backfill all other sunken areas up to original ground levels. So you see that sometimes the recovery stages taken a lot of construction activities compared if we prepare from the early stage before construction started. So there are few things need to be done after failure occurred, and this is talking about the projections of the time frame of the project can be affected. What are the additional safety measures? For example, to carry out checks and further reviews on the design and constructions of their temporary work, and then check with the land transportations, their requirement and guidelines, and any other things that related to the site constructions area. So what are the lessons learned? So these are something mentioned from any other articles. Firstly is the effective risk management. So the potential for major accident should be observed whether due to construction process or deficit in design. And then the owner of the buildings management must seek a balance between production pressures and the quality and the safety goals, robustness of the design. So it is very essential, and the design should be sufficient redundancy to prevent a catastrophic collapse in the event of failure or any particular element. And the temporary works for deep excavation should be given the same respect as permanent works. And finally, is a numerical analysis should be supplement and not supplant sound engineering judgment and practice. So those who perform geotechnical analysis must be capable to validate and verify the results. So back analysis, it is a proper back analysis should be done with an understanding of why the design is not performing as originally predicted, and not just to increase the design levels. For example, the input parameters should be adjusted to allow for the displacement and forces to fit the measurement. So this means that when we are doing the monitoring on site during the constructions, it means that we can change our design accordingly to the real-time field data. So it's not saying that the first design we propose or we started our construction that will be last until the construction complete. No, it can be changed accordingly to the monitoring site data. Okay, in summary, need to choose appropriate soil model to predict soil behavior in undrained shear strength of the soil. And for undrained shear strength, more column give over predicted results. On soil strength, however, give underestimated active earth pressure from this case. And modified Chemplay and original Chemplay is more suitable and give close result even though the calculation analysis was carried out by undrained shear strength with effective stress analysis. Understanding of the excavation process, redistribution of strut forces, and progressive failure are important. So these are the 4 important summaries that we can capture or we can obtain from the case study of Nickel Highway. So the excavation process is very tedious, but we have to treat as a permanent structure, not as a temporary structure. So do you have any more questions?
Ada.
Okay, for your assignment 2, saya dah post dalam your future, on your future. Assignment 2, dia tak terlibat dengan excavations. You can focus on the slope stability, which is in our last chapter. So that is more important for assignment 2. And then what are the importance about slope stability is part of the shear strength value. Right now, the shear strength for slope stability is not only focusing on saturated condition, it also can be calculated using the unsaturated conditions. So we end our lecture tonight here at the sections Nickel Highway collapse in the case study for chapter 4. Okay, if we do not have any further discussions, I would like to excuse myself from the class.
Doktor tak mau baca soalan assignment 2 sama-sama ke?
Alamak, soalan dekat mana? Soalan tu a bit familiar. Saya punya hint senang je. You cari senior awak SEM lepas 4 tahun ke siapa kan. Tanya dia projek depa semester lepas mana?
Okay, thank you Doktor.
Senang je semua. Projek depa tu assignment awak.
Okay, baik-baik. Thank you Doktor.
Cumanya mungkinlah apa yang mereka bagi taklah kata tepat, tapi bolehlah ada discussions kan. I mean that from their report project last semester, mungkin ada improvement kan untuk this semester. Takkanlah you nak submit exactly from the last semester kan. Supposedly upgrade lah sikit kan. But the thing is that yang tu soalan dia sama je macam project dia semester lepas.
Alright Doktor.
Slope stability, dia punya case study dekat Putrajaya. You cari je back analysis or case study in Putrajaya for slope failure.
Okay.
Alright. Thank you.
Terima kasih Doktor. Okay. Good night.
Assalamualaikum.
Salam.